Okay, an introduction to the history of psychology, Chapter 8, Physiology and Psychophysics. Scientific achievements of the 17th and 18th centuries allow long-standing philosophical questions to be answered in new, more precise ways. Much has been learned about the physical world, and it was now time to direct scientific method towards the study of physiological mechanisms by which we come to know the physical world. Basically, the question was, how do external events come to be represented in consciousness? Everything from sense perception to motor reactions was studied intensely, and this study eventually gave birth to experimental psychology. If we're interested in discovering the origins of matters that are central to psychology, we need to go back to the early Greeks. If, however, we are interested in the origins of experimental psychology, we must look to early developments in other empirical sciences, such as physiology, anatomy, neurology, and even physics and astronomy. Objective and subjective differences. It was astronomers who first realized that the type of knowledge human physiology provided might be useful to all sciences, and in 1795, astronomer Neil Maskelyne and his assistant David Kinnebrook were setting ship's clocks according to when a particular star was observed So we're setting ship's clocks according to when a particular star crossed a hairline in a telescope. Maskelyne noticed that Kinnebrook's observations were about a half second slower than his. Kinnebrook was warned of his error and attempted to correct it. Instead, however, the discrepancy between his observations and Maskelyne's increased by 0.8 of a second, and Kinnebrook was relieved of his duty. 20 years later, the incident came to the attention of a German astronomer, Friedrich Bessel, in 1784 to 1846, who speculated that the error had not been due to an incompetence, but to individual differences among observers. Bessel set out to compare his observations with those of his colleagues, and indeed found systematic differences among them. This was the first reaction time study, and it was used to correct differences among observers. This was done by calculating personal equations. For example, 0.8 of a second was added to Kinnebrook's reaction time. His observations could be equated by Maskelyne's. Bessel found systematic differences among individuals and the same way to compensate for those differences, but his findings did not have much impact on the early development of experimental psychology. As we will see, the early experimental psychologists were interested in learning what was true about human consciousness in general. Therefore, individual differences found among experimental subjects were generally attributed to sloppy methodology. Later, in psychology's history, after Darwin, the study of individual differences was to be of supreme importance. Besides showing the influence of the observer on observations, the personal equation was important because the quantitative assessment that it allowed began to cast doubt on the claims of Kant and others that psychology could not be a science. In a sense, the physical sciences made scientific psychology inevitable. Once the physical sciences were started and well underway, it was inevitable that scientific psychology would arise. The older sciences themselves made it necessary. Investigators were repeatedly having their attention drawn to the observing organism and to the necessity of taking its reactions into consideration in order to make their own accounts exact and complete. Discrepancy in reality. Of course, the demonstration of any discrepancy between a physical event and the person's perception of the event was of great concern to the natural scientists, who believed that their job would accurately describe the explaining the physical world. The problem created by Galileo and Locke's distinction between primary and secondary qualities could be avoided by simply concentrating on primary qualities. That is, concentrating on events for which there was a match between their physical qualities and the sensations that they create. It was becoming increasingly clear, however, that the mismatch between physical events and the perceptions of those events was widespread. Newton had observed that the experience of white light is really a composite of all colors of the spectrum, although the individual colors themselves are not perceived. And in 1760, van Musschenbroek discovered that if complementary colors such as yellow and blue were presented in proper proportions on a rapid rotating disk, an observer sees neither yellow nor blue but gray. It was evident that often there was not a point-to-point correspondence between physical reality and the psychological experience of that reality. Because the most likely source of the discrepancy was the responding organism, physical scientists had reason to be interested in physiology, which studied the biological processes by which organisms interact with the physical world. The physiologist studied the nature of nerves, neural conduction, reflexive behavior, sensory perception, brain functioning, and eventually the systematic relationship between sensory stimulation and sensation. It was the work of physiologists that provided the link between the questions of philosophy and the soon-to-be science of psychology. Thus, to a large extent, both the content of what was to become psychology and the methodologies used to explore that content were furnished by physiology. Bell-Magendie law. Until the 19th century, two views prevailed about what nerves were. One was Descartes' view that the nerve consisted of fibers that connected sense receptors to the brain. These fibers were housed in hollow tubes that in turn transmitted the animal spirits from the brain to the muscles. The second was Hartley's view that nerves were the means by which vibrations were conducted from the sense receptors to the brain and from the brain to the muscles. And in 1811, the great British physiologist Charles Bell, printed 1774 to 1842, printed and distributed to his friends 100 copies of a pamphlet that summarized his groundbreaking research on the anatomical and functional discretenesses of sensory and motor nerves. Operating on rabbits, Bell demonstrated that sensory nerves enter the posterior or dorsal roots of the spinal cord, and the motor neurons emerged from the anterior ventral roots. Bell's discovery separated nerve physiology into the study of sensory and motor functions, that is, into a study of sensation and movement. Bell's specific mental functions were mediated by different anatomical structures. That there are sensory and motor nerves is actually an idea articulated from empirical observations as far back as Eratosthenes, of Alexandria, and reinforced by Galen's study of gladiators and soldiers in the 2nd century A.D. It was Bell, however, who provided the scientists of the day with clear-cut experimental evidence. As mentioned, Bell circulated his findings among his friends. This explains why the prominent French physiologist François Magendie, 1783 to 1855, could publish similar results 11 years later without being aware of Bell's findings. A heated debate arose among Bell and Magendie's followers about the priority of the discovery. History settled the issue by referring to the discovery as the Bell-Magendie law. For more details about the controversy, see Cranfield, 1974. After Bell and Magendie, it was no longer possible to think that nerves as general conveyors of vibration or spirits. Now, the law of forward direction governed the nervous system. Sensory nerves carried impulses from the sense receptors to the brain, and the motor nerves carried impulses forward from the brain to the muscles and glands. The Bell-Magendie law demonstrated separate sensory and motor tracts in the spinal cord and suggested separate sensory and motor regions of the brain. Doctrine of specific nerve energies. Born in Koblenz, Germany, the famed physiologist Johannes Müller, 1809 to 1858, expanded the Bell-Magendy law by devising the doctrine of specific nerve energies. After receiving his doctrine from the University of Bonn in 1822, Müller remained there as a professional until 1833, when he accepted the newly created chair of physiology at the University of Berlin. Following Bell's suggestion, Müller demonstrated that there are different types of sensory nerves, each containing a characteristic energy, and that when they are stimulated, a characteristic sensation results. In other words, each nerve responds to its own characteristic way, no matter how it is stimulated. For example, stimulating the eye with light waves, electricity, pressure, or by a blow to the head will cause visual sensations. Emile Desbois Raymond, 1818 to 1896, one of Müller's students, went so far as to say that if we could cut across the visual and auditory nerves, we would hear with our eyes and see with our ears. Adequate stimulation. Although Müller claimed that various nerves contain their own specific energy, he did not think that all sense organs were equally sensitive to the same type of stimulation. Rather, each type of sense organ is maximally sensitive to a certain type of stimulation. Müller called this specific irritability, and it was later referred to as adequate stimulation. The eye was most easily stimulated by light waves, and the ear by sound waves, and the skin by pressure, and so on. So the eyes can be stimulated by pressure, but pressure is less adequate stimulus for vision than is a light wave. As we experience the environment, the differential sensitivity of the various senses provide an array of sensations. In this way, a picture of the physical environment is formed. But the nature of the picture, for example, how articulated it is, depends on the sensory systems that humans possess. For Müller, then, the correspondence between the sensations and the objects of the physical world is determined by our senses and their specific irritability. Müller agonized over the question of whether the characteristics of the nerves itself or the place of the brain where the nerve terminates accounts for specificity. He concluded that the nerve was responsible, but subsequent research proved that the brain location is the determinant. Consciousness, sensations, and reality. The most significant implication of Müller's doctrine for psychology was that the nature of the central nervous system, not the nature of the physical stimulus, determines our sensations. Müller's findings underscored that we're never conscious of objects in the physical world, but the various sensory impulses in the brain linked to those real objects. It follows that our knowledge of the physical world must be limited to the type of sense receptors we possess. An ardent Kantian, Müller believed that he had found the physiological equivalent of Kant's categories of thought. According to Kant, sensory information was transformed by the innate categories of thought before it is experienced consciously. And for Müller, the nervous system is the interdeterminary between physical objects and consciousness. Kant's nativism stressed mental categories, whereas Müller's stressed physiological mechanisms. In both cases, sensory information is modified, and therefore what we experience consciously is different from what is physically present. For Müller, however, sensations did not exhaust mental life. In his book, Handbuch der Physiologie der Menschwesen, this isn't in German. Come on now. Handbook of Human Physiology, English. In the section titled Of the Mind, he postulated a mind capable of attending to some sensations. The mind capable of attending to some sensations to the exclusion of others. Thus, even in his otherwise mechanistic system, Müller found room for an active mind. Again in allegiance with Kant. Müller was one of the greatest experimental physiologists ever, which I would like to highlight. The highlighter that I can't find. Yeah, His handbook summarized what was known about human physiology at the time. Mueller also established the world's first institute of experimental physiology at the University of Berlin. Mueller understood the close relationship between physiology and psychology. He said, nobody can be a psychologist unless they first become a physiologist. Hermann von Helmholtz. Many consider Hermann von Helmholtz 1821 to 1894 to be the premier scientist of the 19th century. As we will see, he made significant contributions in physics, physiology, and psychology. Helmholtz, born in Potsdam, Germany, was a frail child with a mediocre student who was especially poor at foreign languages and poetry. Helmholtz's apparent mediocrity as a student, however, seemed to reflect the inadequacy of his teachers, because he spent his spare time reading scientific books and working out the geometrical principles that described the various configuration of his play blocks. His father was a teacher who did not have enough money to pay for scientific training that his son desired. Fortunately, the government had a program under which talented students could go to medical school free if they agreed to serve for 8 years as army surgeons following graduation. Helmholtz took advantage of this program and enrolled in the Berlin Royal Friedrich Wilhelm Institute of Medicine and Surgery when he was 17 years old. While in his second year of medical school, he began his studies with Johannes Mueller. Helmholtz stand against vitalism. Although Helmholtz accepted many of Mueller's conclusions, the two men still had basic disagreements, one of them over Mueller's belief in vitalism. In biology and physiology, the vitalism-materialism problem was much like the mind-body problem in philosophy and psychology. Vitalists maintained that life could not be explained by interactions of the physical and chemical processes alone. For vitalists, life was more than a physical process and could not be reduced to such a process. Furthermore, because it was not physical, the life force was forever beyond the scope of scientific analysis. Mueller was a vitalist. Controversially, the materialists saw nothing mysterious about life and assumed that it could be explained in terms of physical and chemical processes. Therefore, there was no reason to exclude the study of life or of anything else for the realm of science. Helmholtz sided with the materialists who believed that the same laws apply to living and non-living things, as well as to mental and non-mental events. Mental, as well as to mental and non-mental events. So strongly did Helmholtz and several of his fellow students believe in materialism that they signed the following oath, and some say in their own blood. Here it is. No one forces than the common physical-chemical ones are active within the organism. In those cases, we cannot, at the time, be explained by these factors, one of either to find a specific way or form of their specific action by means of the physical mathematical method, or to assume new forces equal in dignity to the physical chemical forces inherent in matter, reducible to the force of attraction and repulsion. Does not seem significant enough to be signed in blood. Personal opinion. But anyways, in addition to Helmholtz, others who signed the oath were Du Bois-Reymond, who became a professor of physiology at the University of Berlin when Mueller died, Carl Ludwig, who became a professor of physiology at the University of Leipzig, where he influenced young Ivan Pavlov, and Ernst Brücke, who became a professor of physiology at the University of Vienna, where he taught and befriended Sigmund Freud. What this group accepted when they rejected vitalism were the beliefs that living organisms, including humans, were complex mechanism. and that these machines consist of nothing but material substances. Materialism. And so the mechanistic, materialistic philosophy embraced by these individuals profoundly influenced physiology, medicine, and psychology. Okay. Principle of conservation of energy. Helmholtz obtained his medical degree at the age of 21 and was inducted into the Army. While in the Army, he was able to build a small laboratory and continue his early research, which concerned metabolic processes in the frog. Helmholtz demonstrated that food and oxygen consumption were able to account for the total energy that an organism expended, and thus able to apply the already popular principle of conservation. Principle of conservation of energy to living organisms. According to this principle, which has previously been applied to the physical phenomena, energy is never created or lost in a system, but is only transformed from one form to another. When applied to living organisms, the principle was clearly in accordance with the materialistic philosophy because it brought physics, chemistry, and physiology close together. And in 1847, Helmholtz published a paper titled The Conservation of Force, and it was so influential that he was released from the remainder of his tour of duty in the Army. And in 1848, Helmholtz was appointed lecturer of anatomy at the Academy of Arts in Berlin. The following year, he was appointed professor of physiology at Königsberg, where Kant had spent his entire academic life. It was at Königsberg that Helmholtz conducted his now famous research on the speed of nerve conduction. So, rate of nerve conduction. Mueller maintained that nerve conduction was almost instantaneous, making it too fast to measure. This view reflected his belief that there was a vital non-material agent that moved instantaneously and determined the behavior of living organisms. Those believing in such vital force never considered measuring the speed of nerve conduction. So Helmholtz, however, excluded nothing from the realm of science, not even the rate of nerve conduction. To measure the rate, where was I? To measure the rate, Helmholtz isolated a nerve fiber leading to a frog's leg muscle. He then stimulated the nerve fiber at various distances from the muscle and noted how long it took for the muscle to respond. He found that the muscular response followed more quickly when the motor nerve was stimulated closer to the muscle than when it was stimulated farther from the muscle. By subtracting one reaction time from the other, he concluded that the nerve impulse travels at the rate of about 90 feet per second. Which is 27.4 meters per second. Helmholtz then turned to humans, asking his subjects to respond by pushing a button when they felt their leg being stimulated. He found that reaction time was slower when the toe was simulated than when the thigh was simulated. He concluded again, by subtraction, that the rate of nerve conduction in humans was between 165 to 330 feet per second, or 50.3 to 100.6 meters per second. This aspect of Helmholtz's research was significant because it showed that nerve impulses are indeed measurable, and in fact, they are relatively slow. This was taken as further evidence of the physical-chemical processes are involved in our interactions with the environment, instead of some mysterious process that was immune to scientific scrutiny. Although to measure reaction time was extremely useful for Helmholtz in measuring the speed of nerve conduction, he found that it varied considerably among subjects, and even for the same subject at different times. So he concluded that the reaction time was too unreliable to be used as valid measure, and he abandoned it. Support for his doubts came later, when more precise measurements made by Du Bois-Reymond indicated that the nerve conduction speed he had reported were too slow. But this does not detract from the importance of Helmholtz's pioneering research. Theory of perception. Although he believed that the physiological apparatus of the body provides the mechanism for sensation, Helmholtz thought that the past experience of the observer is what converts a sensation into a perception. Sensations, then, are the raw elements of conscious experience, and perceptions are sensations after they are given meaning by one's past experiences. I'm going to highlight that. Okay. In explaining the transformation of sensations into perceptions, Helmholtz relied heavily on the notion of unconscious interference. According to Helmholtz, to label a visual experience a chair involves applying a great deal of previous experience, as does looking at railroad tracks converging in the distance and insisting that they are parallel. Similarly, we see moving pictures as moving because our prior experience with events that create a series of images across the retina. We learn from experience that perceived distance is inversely related to the size of the retinal image. Helmholtz decided that the perception of depth arises because the retinal image, an object, causes a slightly different in two different retinas. Previous experience with such retinal disparity causes the unconscious interference of depth. Helmholtz was reluctant to use the term unconscious interference because it suggested the type of mysterious process of the world that would violate his oath, but he could not find a better term. It's okay, homie. It's okay. Helmholtz supported his empirical theory of perception with the observation that individuals who are blind at birth then acquire sight needs to learn to perceive. Even though all of the sensations furnished by the visual apparatus are available, his classic experiments with lenses that distorted visions provided further evidence. Helmholtz had subjects wear glasses and displace the visual field several inches to the right or to the left. At first, the subject would make mistakes in reaching for objects, but after several minutes, perceptual adaptation occurred. While even wearing the glasses, the subjects could again interact accurately with the environment. So when the glasses were removed, the subjects again made mistakes for a short period of time soon after they recovered. Helmholtz took several innate categories of thought Kant had proposed and showed how they were derived from experience. Helmholtz and Kant agreed on one important point. The perceiver transforms the senses, what the senses provide. For Kant, this transformation was accomplished when sensory information was structured by the innate faculties of the mind. But for Helmholtz, the transformation occurred when the sensory information was embellished by an individual's past experiences. With his notion of unconscious interference, Helmholtz came very close to what we would later be considered a part of psychology. That is, for unconscious interference to convert a sensation into perception. Memories of the learning experiences must interact with current sensations. Although the processes of learning and memory were later to become central in psychology, Helmholtz never considered himself a psychologist. He believed that psychology was too closely allied with metaphysics, and he wanted nothing to do with metaphysics. All right, so theory of color vision. Helmholtz performed his work on vision between 1853 to 1868 at the University of Königsberg, Bonn, and Heidelberg, and he published his results in the 3-volume Handbook of Physiological Optics. Many years before Helmholtz's birth, Thomas Young had proposed a theory of color vision very similar to Helmholtz. But Young's theory had not been widely accepted. Helmholtz changed Young's theory slightly and buttressed it with experimental evidence. The theory we present here has come to be called the Young-Helmholtz theory of color vision, also called trichromatic theory. And in 1672, Newton had shown that the white sunlight passed through a prism, it emerged as a band of colored lights, with red on one end of the band, then orange, yellow, green, blue, indigo, and finally violet. The prism separated the various wavelengths that together were experienced as white. Early speculation was that different wavelengths corresponded to each color, and that different color experiences resulted from experiencing different wavelengths. However, Newton himself saw difficulties with this explanation. He mixed various wavelengths, and it became clear to him that the property of color was not in the wavelengths themselves, but in the observer. For example, white is experienced either if all wavelengths of a spectrum are present, or if wavelengths corresponding to colors red and blue-green are combined. Similarly, a person cannot distinguish the sensation of orange caused by the single wavelength corresponding to orange from the sensation of orange caused by mixing red and yellow. The question was how to account for the lack of correspondence between the physical stimuli present and the sensations that they caused. Helmholtz's answer was to expand on Müller's doctrine of specific nerves. Specific nerve energies by postulating 3 different types of color receptors on the retina. That is, instead of saying that color vision had one specific nerve energy associated with it, as Müller had thought, Helmholtz claimed it involved 3 separate receptors, each with its own specific energy. It was already known that various combinations of 3 colors, red, green, and blue-violet, the additional primary colors, It was already known that the various combinations of 3 colors, red, green, and blue-violet, the additive primary colors, so those are the additive primary colors, I got it, could produce all other colors. Helmholtz speculated that there were 3 types of color receptors corresponding with the 3 primary colors. If a red light is shown, the so-called red receptors are stimulated, and one has the sensation of red. If the green light is shown, the green receptors are stimulated, and one has the experience of green, and so on. If all these primaries are shown at once, one experiences white. If the color shown is not a primary color, it would simulate various combinations of the 3 receptors, resulting in a subjective color experience corresponding to the combination of wavelengths present. For example, presenting a red and a green light simultaneously will produce the subjective color experience of yellow. Also, the same color experience could be caused by several different patterns of light, the 3 receptor systems firing. And in this way, Helmholtz explained why many physical wavelengths give rise to the same color experience. The young Helmholtz theory of color vision was extremely helpful in explaining many forms of color blindness. For example, if a person lacks one or more of the receptor systems corresponding to primary colors, he or she will not be able to experience certain colors subjectively. Even though the physical world has not changed, the senses therefore actualize elements of the physical world that otherwise exist only as potential experiences. Helmholtz was continually amazed at the way physiological mechanisms distort the information a person receives from the physical world. But he was even more amazed at the mismatch between physical events and psychological sensations, such as the experience of color. Helmholtz expressed his feelings as follows. The inaccuracies and imperfections of the eye as an optical instrument are deficiencies of the image on the retina, now appear insignificant in comparison with the incongruities we have met with in the field of sensation. One might almost believe that nature had here contradicted herself on purpose in order to destroy any dream of pre-existing harmony between the outer and the inner world. Theory of auditory perception. For audition, as he had done for the color vision, Helmholtz further refined Müller's doctrine of specific nerve energies. He found that the ear is not a single sense receptor, but a highly complex system of many receptors. Whereas the visual system consists of 3 types of nerve fibers, each with their own specific nerve energy, the auditory system contains thousands of types of nerve fibers, each with their own specific nerve energy. Helmholtz found that the main membrane of the inner ear and the basilar membrane was removed and uncoiled, it would be shaped much like a harp. Assuming that the membrane is to hearing what the retina is to seeing, Helmholtz speculated that the different fibers along the basilar membrane are sensitive to different frequencies of sound. The short fibers respond to the higher frequencies, and the long fibers respond to the lower frequencies. A wave of certain frequency causes the appropriate fiber of the basilar membrane to vibrate, thus causing the sensation of sound corresponding to the frequency. This process is called sympathetic vibration. And it is demonstrated by stimulating a tuning fork of a certain frequency and noting that the strings on the piano correspond to that frequency also begins to vibrate. Helmholtz assumed a similar process occurs in the middle ear, and that through various combinations of fiber stimulation, one could explain a wide variety of auditory experiences we have. This theory is referred to as the resonance place theory of auditory perception. Variations of Helmholtz place theory persist today. Helmholtz contributions. Although Helmholtz was an empiricist, his explanations of sensation and perception, in his explanations of sensation and perception, he did reflect the German zeitgeist by postulating an active mind. According to Helmholtz, the mind's task was to create a reasonably accurate conception of reality from the various signs that it receives from the body's sensory systems. Thank you. Helmholtz assumed that the dynamic relationship exists among volition, sensation, and reflection of the mind, attempts to create a functional view of external reality. Helmholtz's view of the mind differed from that of most of the British empiricists and French sensationalists, because he saw the mind as largely passive. For Helmholtz, the mind's job was to construct a workable concentration of reality given the incomplete and perhaps distorted information furnished by the senses. Although Helmholtz did postulate an active mind, he accepted an empirical explanation of the origins of the contents of the mind. In his explanations of sensation, the mental events that result from sensory stimulation, and perception, which is the sensation plus unconscious inference. Helmholtz was emphatically empirical and unequivocally scientific. He showed that nerve transmission is not instantaneous, and had previously been believed, but that it was rather slow and reflects the operation of the physical processes. More than anyone before him, Helmholtz showed with experimental rigor the mechanisms by which to commerce with the physical world, mechanisms that could be explained in terms of objective physical laws. Although he found that the match between what was physically present and what is experienced psychologically is not perfect, he could explain the discrepancy in terms of properties of the receptor system and the unconscious inferences of the observer. No mystical, unscientific forces were involved. Helmholtz brought physics, chemistry, and physiology and psychology closer together. In so doing, he paved the way for the emergence of experimental psychology, which was in many ways an inevitable step after Helmholtz's work. For an excellent discussion of Helmholtz's contributions to modern science and of the cultural climate by which they were made, see Hergenhahn, 1994. Helmholtz realized a lifelong ambition when he was appointed professor of physics at the University of Berlin in 1871. And in 1882, the German emperor granted him noble status, and thereafter his name, Hermann von Helmholtz. Wasn't that his name before? What? Hold on. What was his? That was his name before. And thereafter his name was Hermann von Helmholtz. Just the same as it says. Okay. Cool. In 1893, Helmholtz came to the United States to see Chicago World's Fair and to visit with William James. On his way back to Germany, he fell aboard ship and suffered cuts and bruises, was apparently not badly injured. Following the incident, however, he complained about a general lack of energy. The next year, he suffered a cerebral hemorrhage and died on September 8, 1894. R.I.P. Helmholtz.
Ewald Hering. Helmholtz, with his notion of unconscious inference, generally sided with those who said perceptions were learned. Ewald Hering, 1834 to 1918, sided with the nativists. After receiving his medical degree from the University of Leipzig, Hering stayed there for several years before accepting a post as lecturer at the Vienna Military Medical Academy, where he worked with Joseph Breuer, 1842 to 1952, who was later to be instrumental in the founding of psychoanalysis. Working together, Hering and Breuer showed that respiration was, in part, caused by the receptors in the lungs, a finding called the Hering-Breuer reflex. And in 1870, Hering was called to the University of Prague, where he succeeded the great physiologist Jan E. Purkinje, 1787 to 1869, Lake Goethe, with whom Purkinje dedicated one of his major works. Purkinje was a phenomenologist. He believed that phenomenon on the mind arrived at by careful introspective analysis should be what physiologists attempt to explain. According to Purkinje, the physiologist is obligated to explain not only normal sensations and perceptions, but abnormal ones as well. Such as illusions and after images. Among many phenomena that Purkinje observed was the relative vividness of colors in different in faint light. Vividness of colors indifferent in faint light than it is in the bright light. More specifically, as twilight approaches, hues that correspond with short wavelengths such as violet and blue appear brighter than hues corresponding with wavelengths such as yellow and red. This change in relative vividness as a function of luminance level is known as the Purkinje shift. Herring also was a phenomenologist, and in his theory of color vision was based largely to scratch that. I can't think right now. His theory of color vision was based to a large extent on the phenomenon of negative after images. Space perception and color vision on the matter of space perception, we have seen that Helmholtz believed that it solely develops from experience as physiological and psychological events are correlated. Herring, however, believed that when stimulated, each point on the retina automatically provides three types of information about the stimulus: height, left-right position, and depth. Following Kant, Herring believed that space perception exists a priori. For Kant, space perception was an innate category of the mind. For Herring, it was an innate characteristic of the eye. This controversy about perception became the Helmholtz-Herring debate in various guises, continues even today. After working on the problem of space perception for about 10 years, Herring turned to color vision. Herring observed a number of phenomena that he believed either were incompatible with young Helmholtz theory or could not be explained by it. He noted that certain pairs of colors, when mixed together, give the sensation of gray. This was true for red and green, blue and yellow, and black and white. He also observed that a person who stares at red and then looks away experiences a green after image. Similarly, blues give a yellow after image. Herring also noted that individuals who have difficulty distinguishing red from green could still see yellow. It is also typical for a colorblind person to lose sensation in both red and green, not just one or the other. All of these observations at least posed problems for the young Helmholtz theory, if they did not contradict it. To account for these phenomena, Herring theorized that there are three types of receptors on the retina, and that each could respond in two ways. One type of receptor responds to red-green, one type to yellow-blue, and one type to black and white. Red, yellow, and white cause a tearing down, or the catabolic process in the respective receptors. Green, blue, and black cause a building up, or anabolic process in their respective receptors. In both colors to which a receptor is sensitive are experienced simultaneously. The catabolic and anabolic processes are canceled out. Had to put my glasses on. Makes all the difference. All right, so the catabolic and anabolic processes are canceled out, and the sensation of gray results. If one color to which a receptor is sensitive is experienced, its corresponding process is depleted, leaving only its opposite to produce an after image. Finally, Herring's theory explained why individuals who cannot respond to red and green can still see yellow, and why the inability to see red is usually accompanied by the inability to see green. For nearly 50 years, lively debate ensued between those accepting the young Helmholtz theory and those accepting Herring's. The matter is still far from settled. The current view is that young Helmholtz theory is correct in that there are retinal cells sensitive to red and green and blue, but that there are neural processes beyond the retina that are more in accordance with Herring's proposed metabolic processes. Kristen Ladd Franklin. Throughout Western history, neither philosophy nor science has been common vocations for women. In both ancient Egypt and Greece, there was some famous women physicians, but we know little about their names. Educational opportunities were rare for most anyone in medieval Europe, but especially for women. The extensive writings of Hildegard of Bingen, died 1179, is often cited as the lone notable exception. With the advent of printing in the Renaissance, education and literacy again was on the rise, even for women. By the 1700s and the 1800s, a few women were gaining modest recognition in philosophy and science. For example, Italian Laura Bassi, 1711 to 1778, is thought to have been the first female university professor. As psychology finally found its place among the academic sciences, so too did women. Christine Ladd, 1847 to 1930, graduated from the then new Vassar College in 1869. She pursued her interest in mathematics, but also knew Johns Hopkins University, and although she completed all the requirements for a doctorate in 1882, the degree was not granted because she was a woman. She has, however, given an honorary degree by Vassar in 1887, when the social climate became less discriminating against women. She was granted her doctorate from Johns Hopkins in 1926, 44 years after she had completed her graduate work. She was nearly 80 years old at the time. And in 1882, Christine Ladd married Fabian Franklin, a mathematics professor at Johns Hopkins. During her husband's sabbatical leave in Germany, Christine Ladd Franklin was able to pursue an interest in psychology. She had published a paper on vision in 1887. Although at the time women were generally excluded from German universities, she managed to be accepted for a year, 1891 to 1892. In George E. Mueller's laboratory at Göttingen, where Hering's theory of color was supported. After her year under Mueller's influence, she studied with Helmholtz at the University of Berlin, where she learned about the trichromatic theory of color vision. Before leaving Europe, Ladd Franklin was already to announce her own theory of color vision, which she believed improved upon those of Helmholtz and Hering. She presented her theory at the International Congress of Experimental Psychology in London in 1892. Upon returning to the United States, Ladd Franklin lectured logic and psychology at Johns Hopkins until she and her husband moved to New York, where she lectured and promoted her theory of color vision at Columbia University in 1910 until her death in 1930. Ladd Franklin's theory of color vision was based on evolutionary theory. She noted that some animals are colorblind and assumed that achromatic vision appeared first in evolution and color vision came later. She assumed further that the human eye carries vestiges of its earlier evolutionary development. She observed that the most highly evolved part of the eye is the fova, where, at least in daylight, visual acuity and color sensitivity are greatest. Moving from the fova to the periphery of the retina, acuity is reduced and the ability to distinguish colors is lost. However, in the periphery of the retina, night vision and movement perception are better than in the fova. Ladd Franklin assumed that peripheral vision provided by the rods of the retina was more primitive than foveal vision provided by the cones in the retina. Because night vision and movement detection are crucial for survival. But if color vision evolved later than the achromatic vision,
Was it not possible that color vision itself evolved in progressive stages? After carefully studying the established color zones on the retina and the fact of color blindness, Lad Franklin concluded that color vision evolved in 3 stages. The achromatic vision came first, and then blue-yellow sensitivity, and finally red-green sensitivity. The assumption that the last to evolve would be the most fragile explains the prevalence of red-green color blindness. Blue-yellow color blindness is less frequent because it evolved earlier and is less likely to be defective. Achromatic vision is the oldest and therefore most difficult to disrupt. Lad Franklin, of course, was aware of Helmholtz and Hering's theories, and although she preferred Hering's theory, her theory was not offered in opposition to either. Rather, she attempted to explain in evolutionary terms the origins of the anatomy of the eye and its visual abilities. After the initial popularity, Lad Franklin's theory fell into neglect, perhaps because she did not have adequate research facilities available to her. Some believe, however, that her analysis of color vision still has validity. For interesting biological sketches of Lad Franklin, see Furumoto, 1992, and Scarborough and Furumoto in 1987. So, early research on brain functioning. Toward the end of the 18th century, it was widely believed that a person's character could be determined by analyzing his or her facial features, body structure, and habitual patterns of posture and movement, such as analysis called physiognometry. One version of physiognometry that became extremely popular was phrenology. Phrenology. Not long after Reed and Company had listed what they had thought were the faculties of the mind, others were to take faculty psychology to the realm of physiology. One was Franz Joseph Gall, 1758 to 1828. Gall accepted the widely held belief that faculties of the mind acted on and transformed sensory information, but he made 3 additional claims that changed the history of faculty psychology. The mental faculties do not exist in the same extent in all humans. The faculties are housed in specific areas of the brain. If the faculty was well developed, a person would have a bump or a protrusion on the corresponding part of the skull. Similarly, if the faculty is underdeveloped, a hollow or depression would be in the corresponding part of the skull. Thus, Gall believed in the magnitude of one's faculties could be determined by examining the bumps and depressions on one's skulls. Such an analysis is called phrenology. Gall's idea was not necessarily a bad one. In fact, Gall was among the first to attempt to relate certain personality traits and overt behavior patterns to specific brain functions. The problem was the type of evidence he accepted to demonstrate this relationship. He would observe that someone had pronounced personality characteristic and a well-developed brain structure, and then attribute one to the other. After observing such a relationship with one individual, he would generalize it to all individuals. In their research on the mental faculties, some of Gall's followers exceeded even his shoddiness. If Gall was cavalier in his interpretations of evidence, he attracted some followers who raised that tendency to an art form. When a cast of Napoleon's right skull predicted qualities marked by variance with the emperor's known personality, one phrenologist replied that his dominant side had been the left, a cast of which was conveniently missing. When Descartes' skull was examined, they found deficient in the regions of reason and reflection. Phrenologists reported that the philosopher's rationality had always been overrated. Although Gall was usually reviewed negatively in the history of psychology, he made several positive contributions to the study of brain functioning. For example, he studied that brains of several animal species, including humans, were the first to suggest a relationship between cortical development and mental functioning. He found that larger, better developed cortices were associated with more intelligent behavior. In addition, he was the first to distinguish the functions of gray matter and white matter in the brain. These discoveries alone qualify Gall for recognition in the history of psychology, but there is more. As the 19th century began, the idea of different cortical regions are the idea that different cortical regions are associated with different functions as becoming popular. This, in large part, was due to Gall. In the minds of most historians, Gall, more than any other scientist, put the concept of cortical localization into play. The popularity of phrenology. The term phrenology was actually coined by Thomas Foster in 1815. Gall rejected the term. He preferred physiognomy, physiognomy, whatever. But it was accepted and made popular by his student and colleague Johann Caspar Spurzheim, 1776 to 1832. The dissemination of phrenology into English-speaking countries was facilitated by Spurzheim's The Physiognomical System of Dr. Gall's and Spurzheim, 1815, and by the translation of Gall's on the functions of the brain and each of its parts, with the observations on the possibility of determining instincts, propensities, and talents, or the moral and intellectual dispositions of men and animals by the configuration of the brain and head. Phrenology became enormously popular and was embraced by some of the leading intellectuals in Europe, such as Bain and Comte. One reason for the popularity of phrenology was Gall's considerable reputation. Another was that phrenology provided hope for an objective, materialistic analysis of the mind. The central theme that runs through all the phrenological writings is that man himself could be studied scientifically, and in particular that the phenomena of the mind could be studied objectively and explained in terms of natural causes. Phrenology was also popular because, unlike philosophy, it appeared to offer practical information. For these reasons, phrenology was also embraced enthusiastically in the United States. For example, the Central Phrenological Society, founded in Philadelphia in 1822 by Charles Caldwell, 1772 to 1853. And in 1824, Caldwell published Elements of Phrenology, the first American textbook in phrenology. And in 1827, a second edition of Elements was published. Because of the popularity of phrenology, when Spurzheim arrived in the United States on August 4th, 1832, he was given a hero's welcome, and he lectured at some of the nation's leading universities, such as Harvard and Yale. And his appreciative audiences included physicians, ministers, public educators, college professors, and asylum superintendents. O'Donnell, 1985, points out that these and others were looking to phrenology for a type of information that would later seek in the schools of behaviorism. With or without bumps, phrenology's theory of human nature and personality recommended itself to emerging professional groups searching for positive knowledge. They found in phrenology an etiological explanation of aberrant human behavior, and a predictive technology for assessing character, temperament, and intellect, and a biological blueprint of social reform. The social engineers of the 20th century, together with their patrons and subscribers, would demand no less of modern experimental behaviorism. But the new psychology, or behaviorism, arrived on the American stage, and eager audience anticipated the role it would play. Gall, Spurzheim, and their followers had already written the script. Spurzheim died shortly after he came to the United States. On the day of his funeral on November 17, 1832, the Boston Phrenological Society was formed. Such societies soon sprang up all over the nation, and numerous journals devoted to phrenology emerged in Europe and the United States. One phrenological journal started publishing in 1837 and continued until 1911. In New York, the Fowler brothers and their extended family ran the Institute of Phrenology from 1830s to 1912. They published popular texts and provided services akin to those offered by modern industrial, organizational, and counseling psychologists. A number of phrenology charts began to appear after the publication of Gall's and Spurzheim's books. Proposed a number of faculties ranging from 27, suggested by Gall, to as many as 43, suggested by later phrenologists. Figure 8.1 shows the chart Spurzheim proposed. Look at that. Formal discipline. Phrenology also became highly influential in the realm of education. Several phrenologists made the additional claim that all faculties become stronger with patience, just as muscles do. The belief influenced a number of educators to take a mental muscle approach to education. For them, education meant strengthening mental faculties by practicing the traits associated with them. One could improve one's reasoning ability, for example, by studying mathematics. The belief that educational experiences could be arranged so that they strengthen certain faculties was called a formal discipline. Although Edward L. Thorndike systematically evaluated educational claims of phrenologists and found them to be false. That's the guy. The belief that educational experiences can be arranged to strengthen specific mental faculties persists to the present. In time, the specific claims of phrenologists were rejected, but phrenology did influence a subsequent psychology in a number of important ways. It argued effectively that the mind and the brain are closely related. It simulated intense research on the localization of brain functions, and it showed the importance of furnishing practical information. In other forms of physiognomy itself entered well into the 20th century. William H. Sheldon, 1898 to 1977, was the godson of William James, and following the completion of both his MD and his PhD degrees, he studied with Jung and Freud. Later at Harvard, he became famous for correlating personality with body form. Although eventually reinterpreted by his critics, Sheldon was able to find significant personality differences between thin and angular ectomorphs, lean and muscular mesomorphs, and soft and round mesomorphs. Pierre Flourens. By the turn of the 19th century, it was generally conceded that the brain is an organ of the mind. Under the influence of Gall and other phrenologists, the brain-mind relationship was articulated into a number of faculties housed in specific locations of the brain. Thus, the phrenologists fueled the concern of localization of functions in the brain. Although popular, even among scientists, phrenology was far from universally accepted. A number of prominent physicians questioned the claims of the phrenologists. It was not enough, however, to claim that the phrenologists were wrong in their assumptions. The claim had to be substantiated scientifically. This was the goal of Pierre Flourens in 1794 to 1867. So Pierre Flourens, who used the method of extirpation and ablation in brain research. Extirpation and ablation is a weird word. Ablation involves destroying parts of the brain and noting the behavioral consequences of the loss. As did Gall, Florenz assumed that the brains of lower animals were similar in many ways to human brains, so he used organisms such as dogs and pigeons in his research subjects. He found that the removal of the cerebellum disturbed an organism's coordination and equilibrium. The ablation of the cerebellum resulted in the passivity, and that destruction of the semicircular canals resulted in the loss of balance. When he examined the entire brain, Florenz concluded that there was some localization, but that contrary to what phrenologists believed, the cortical hemisphere functions as a unit. Seeking further evidence of the brain's interrelatedness, Florenz observed that animals sometimes regained functions that they lost following the ablation. Thus, at least some parts of the brain had the capacity to take over functions of the other parts. Florenz's fame as a scientist and his conclusion that the cortex functioned as a unit effectively silenced the phrenologists within the medical community. Subsequent research, however, would show that they had been silenced too quickly. Paul Barocca. On September 13th, 1848, Phineas Gage was working as a railroad construction supervisor when an explosion blew a rod tampering iron through his skull, as shown in Figure 8.2. The sizable rod entered just below his left eye and exited through the top of his head. Amazingly, not only did Gage survive the incident, but he was fully recovered physically. What had changed, however, was Gage's personality. Dr. John Harlow, 1868, observed, "He is fitful, irreverent, indulging at times in the grossest profanity, which was not previously his custom, manifesting but little difference in his fellows, impatient of restraint or advice when it conflicts with his desires, at times pretentiously obstinate, yet capricious and vacillating, devising many plans of future operation. There are no sooner arrangement than they are abandoned." His friends and acquaintances said he was no longer Gage. Modern work based on Gage's skull and Harlow's observations have linked the ablated areas of the brain with corresponding expected behavioral changes. Another person to make such post-mortem correlations was Paul Barocca, 1824 to 1880. Using the clinical method, Barocca cast doubt on Florenz's conclusion about the cortex acted as a whole. Boring, in 1950, described Barocca's observation. Barocca's famous observation was, in itself, very simple, and they had in 1931 been admitted at Bicêtre, an insane hospital near Paris, and a man whose sole defect seemed to be that he could not talk. He communicated intelligently by signs and otherwise mentally normal. He remained at the Bicêtre for 30 years with this defect, and on April 12, 1861, he was put under the care of Barocca, a surgeon, because of a gangrenous infection. Barocca, for 5 days, subjected him to careful examination, in which he satisfied himself with the musculature of the larynx and articulatory organs, and was not hindered by normal movements. And there was no other paralysis that could interfere with his speech. That the man was intelligent enough to speak. On April 17th, the patient, fortunately, it must have seemed for science, died. Within a day, Barocca had performed an autopsy, discovering a lesion in his third frontal convolution of the left cerebral hemisphere. Had presented the brain in alcohol to the Société d'Anthropologie. Actually, even Barocca was not the first to suggest that clinical observations be made and then use autopsy examinations to locate the brain area responsible for the disorder. For example, a French scientist, Jean-Baptiste Bouillard, in 1796 to 1881, had done so as early as 1852. Using the clinical method,
on a large number of cases, Bouillard reached essentially the same conclusion concerning the localization of speech area. On the cortex that Barocca had reached later using the same technique. Why then do we credit Barocca with providing the first credible evidence of cortical localization and not Bouillard? It is primarily because Bouillard had been closely associated with phonology, and by the time that Barocca made his observations, the scientific community was overly cautious about anything or anyone associated in any way with Gall or phonology. In any case, subsequent research confirmed Barocca's observation that a portion of the left cortical hemisphere is implicated in speech articulation or production, and this area is now named Barocca's area. In 1874, just over a decade after Barocca's discovery, a German neurologist, Karl Wernicke, I think is how it's pronounced, 1848 to 1905, discovered a cortical area near Barocca's area, responsible for the speech comprehension. This area is in the left temporal lobe of cortex and has been named Wernicke's area. Barocca's localization of a function on the cortex supported the phrenologist and damaged Floren's contention that the cortex acted as a unit. Unfortunately for phrenologists, however, Barocca did not find the speech area to be where the phrenologist said it would be. Other aspects of Barocca's work were less impressive, reflecting the zeitgeist. He engaged in craniometry, a measurement of the skull and its characteristics, in order to determine the relationship between brain size and intelligence. He began his research with strong conviction that there was such a relationship, but not surprisingly, he found evidence for it. In 1861, Barocca summarized his findings. In general, the brain is larger in mature adults than in the elderly, in men than women, and eminent men than in men of mediocre talent, in superior races than in inferior races. Other things equal is as remarkable relationships between the development of intelligence and the volume of the brain. Barocca was aware of several facts that contradicted his theory. There existed an abundance of large brain criminals, high intelligence women, and small brain people of eminence. And Asians, despite their small average brain size, were generally more intelligent than ethnic groups with larger brains. Take that, guy. In spite of these contradictions, and in the absence of reliable supportive evidence, Barocca continued to believe in the relationship between brain size and intelligence until his death. Then it was discovered that his brain weighed 1428 grams, a bit above average to be sure, but nothing to crow about. So what is the relationship between brain size and intelligence? Deary, 2001, first reviews the contemporary research on the topic and then concludes, there is a modest association between brain size and intelligence. People with bigger brains tend to have higher mental test scores. We do not know yet why this association occurs. Thus it appears that Barocca and other craniometricians were not totally wrong. However, their claim far exceeded their evidence. As we will see in Chapter 10, the tendency to scientifically confirm personal beliefs concerning intelligence continued even when measures of intelligence became more sophisticated. Electrophysiology. Frisch and Hitzig. In 18th century, it was often called the Age of Electricity. There's a scientist's fascination with electricity that soon extended into physiology. In the late 1700s, Luigi Galvini, 1737 to 98, demonstrated that application of the electrical current caused a frog's legs, to twitch. Émile Dubois-Reymond, who was mentioned several times previously, was considered the father of electrophysiology in part for demonstrating the electrical basis for the action potential in nerves and muscles.
Electrically stimulating the exposed cortex of a dog. Gustav Fritz, 1838 to 1927, and Eduard Hitzig, 1838 to 1907, were the two most important, made two important discoveries. First, the cortex is not insensitive, and it has been first the cortex is not insensitive, as has been previously assumed. Second, they found that when certain areas of the cortex are stimulated, muscle movements are elicited from the opposite side of the body, simulating different points in this motor area of the brain, simulated movements from different parts of the body. Thus, another function was localized to the cortex. David Ferrier, 1843 to 1928, refined the cortical research performed by Fritz and Hitzig, using monkeys as subjects and finer electrical stimulation. He was able to produce a more articulated map of the motor cortex, and he was able to elicit behaviors as intricate as the twitch of an eyelid, the flick of an ear, and the movement of one digit. Ferrier then mapped cortical regions corresponding to the cutaneous senses, auditory, olfaction, and eventually vision. He summarized his findings in The Functions of the Brain, 1876, which had a substantial impact on the scientific community. One outcome was that it opened the modern era of neurosurgery. Neurosurgeons were now turned to functional maps in the brain for guidance. The evidence seemed clear. It was a great deal of localization of function on the cortex. But just as the phrenologists had maintained, these findings, however, did not support traditional phrenology. Seldom was the function or faculty found where the phrenologists said it was. Furthermore, the phrenologists had spoken the faculties such as vitality, firmness, love, and kindness. But researchers instead found sensory and motor areas. These findings extended the Bell-Magendie law to the brain. That is, the sensation experience seemed to be more a matter of the cortical area stimulated than a matter of the sensory nerve stimulated. It looked very much as if the brain is a cortex switchboard where sensory information is projected and where in turn stimulates appropriate motor responses. The brain research that was stimulated in the effort to evaluate the claims of the phrenologists made it clear that the physical stimulation gives rise to the various types of subjective experiences and that they are directly related to brain activity. The next step in psychology's development towards becoming an experimental science was to examine scientifically how sensory stimulation is systematically related to conscious experience. The rise of experimental psychology. The very important difference between what is physically present in the world and what is experienced psychologically has been recognized and agonized over for centuries. This was the distinction that had caused Galileo to conclude that the science of psychology was impossible, and Hume to conclude that we could know nothing about the physical world with certainty. Kant amplified this distinction when he claimed that the mind embellished sensory experiences, and Helmholtz reached the same conclusion with his concept of unconscious inference. With advances in science, much had been learned about the physical world, including about the physical stimulation of the sense receptors, which convert to the stimulation of nerve impulses, about the brain structures where those impulses terminate. There was never much doubt about the existence of consciousness. The problem was determining what we were conscious of and what caused that consciousness. By now, it is widely believed that the conscious sensations were triggered by brain processes, which themselves were initiated by a sense reception. But the question remained, how are the two domains, conscious mental events and physiological processes in our sensory system, related? Ernest Heinrich Weber, 1795 to 1878. The contemporary of Johannes Müller, was born in Wittenberg, the son of a theology professor. He was the third of 13 children. Weber obtained his doctorate of the University of Leipzig in 1815 and taught there until his retirement in 1871. Weber was a physiologist who was interested in the senses of touch and kinesis, muscle sense. Most of the research on sense perception before Weber had been confined to vision and audition. Weber's research consisted largely of exploring skin and muscle sensations. Weber was among the first to demonstrate the sense of touch is not one, but several senses. For example, what is ordinarily called the sense of touch includes the senses of pressure, temperament, and pain. Weber also provided convincing evidence that there is a muscle sense. It was in regards to the muscle sense that Weber performed his work, or just noticeable differences, which we will consider shortly. Touch and kinesthesis. I feel like that's how you say that, kinesthesis. For the sensation of touch, Weber attempted to determine the last spatial separation between the 2 points of touch on the body. The 2 points of touch on the body could be discriminated. Using a compass-like device consisting of 2 points, he simultaneously applied 2 points of pressure to the subject's skin. The smallest distance between the 2 points at which the subject reported sensing 2 points instead of 1 was called the 2-point threshold. His famous book, One Touch, Anatomical and Physiological Notes, 1834. Weber provided charts of the entire body with regard to the 2-point threshold. He found the smallest 2-point threshold on the tongue, about 1 millimeter, and the largest in the middle of the back, about 60 millimeters. He assumed that the differences in thresholds at differential places of the body resulted from the anatomical arrangement of the sense receptors for touch. The more receptors, the finer the discrimination. Within the history of psychology, Weber's research on the muscle sense, or kinesthesis, is even more important than his research on touch. It was while investigating kinesthesis that Weber ran his important weight discrimination experiments. In general, he sought to discriminate the smallest difference between 2 weights that could be discriminated. To do this, he had his subjects lift one weight, the standard, which remained the same during a series of comparisons, and then lift other weights. The subject was to report whether the varying weights were heavier, lighter, or the same as the standard weight. He found that when the variable weights were only slightly different from the standard, they were judged to be the same as the standard. Through a series of such comparisons, Weber was able to determine the just noticeable difference, or J&D, between the standard and the variable weight. It is important to note that although Weber did not label them as such, J&Ds were psychological experiences or conscious sensations. Weber ran with the basic weight discrimination experiment under 2 conditions. In one condition, the weights were placed on the subject's hands while the hands were resting on the table. This condition, the subject's judgments were made primarily on the basis of tactile sensations. In the second condition, the subject lifted his hands with the weights on them. In this condition, the subject's judgments were made on the basis of both tactile and kinesthetic sensations. It was found that subjects could detect much smaller weight differences when they lifted the weights than they could when the weights were simply placed in their hands. Weber thought it was the involvement of kinesthesis in the lifted weight condition that provided greater sensitivity to the weight differences. Judgments are relative and not absolute. During his research on kinesthesis, Weber made startling observations that the J&D
is the constant fraction of the standard weight. For lifted weights, the fraction is 1/40th. For non-lifted weights, it is 1/30th. Using the lifted weights, for example, if the standard weight is 40 grams, the variable weight would have to be 41 grams to be judged as heavier, or 39 grams to be judged as lighter than the standard. If the standard weight is 160 grams, then the variable weight would have to be 164 grams or 156 grams to be judged as heavier or lighter, respectively, than the standard. Weber then aligned himself with a large number of scientists and philosophers who found that there was not a simple one-to-one correspondence between the presently physical and what was experienced psychologically. Weber observed that discrimination does not depend on the absolute difference between the two weights, but on the relative difference between the two, or the ratio of one to the other. Weber extended his research to other sense modalities and found evidence that suggested that there is a constant fraction corresponding to J and Ds for each sense modality. To find that J and Ds corresponded to the constant fraction of standard stimulus was later called Weber's law. It can be considered the first quantitative law in psychology's history. This was the first statement of systematic relationship. This is the first quantitative law. First statement of a systematic relationship between the physical stimulation and the psychological experience. But because Weber was a physiologist, psychology was not his primary concern. It was Fechner who realized the implication of Weber's work in psychology and whom saw the possible resolution of the mind-body problem. Gustav Theodor Fechner, 1801 to 1887, was a brilliant, complex, and unusual individual. Fechner's father had succeeded his grandfather as village pastor. After his father died, Fechner, his brother, and his mother spent the next few years with Fechner's uncle, who was also a pastor. And at the age of 16, Fechner began his studies in medicine at the University of Leipzig, where Weber was studying, and attained his medical degree in 1822 at the age of 21. Upon receiving his medical degree, Fechner's interest shifted from biological science to physics and mathematics. At this time, he made a meager living by translating into German certain French handbooks of physics and chemistry, by tutoring and by lecturing occasionally. Fechner was interested in the properties of electric currents, and in 1831 published a significant article on this topic, which established his reputation as a physicist. And in 1832, when he was 33 years old, Fechner was appointed professor of physics at Leipzig. Soon his interest began to turn to the problems of sensation, and by 1840 he had published articles on color vision and after images. Around 1840, Fechner had a nervous breakdown, resigned his position at Leipzig, and became a recluse. Additionally, Fechner had been almost blinded, presumably while looking at the sun through colored glasses during his research on after images. At this time, Fechner entered a state of severe depression that was to last several years and resulted in his interest turning from physics to philosophy. The shift was in emphasis only, however, because throughout his adult life he was uncomfortable with materialism, which he called the night view. It contrasted with the day view, which emphasized mind, spirit, and consciousness. He accepted Spinoza's double aspect view of mind and body, and therefore believed that consciousness is a prevalent in the universe as is matter. Because he believed that consciousness cannot be separated from physical things, his position represents panpsychism. Okay.
That is, all things are physical. All things that are physical are also conscious. In his lifetime, Fechner wrote 183 articles and 81 books and edited many others. He died in his sleep on November 18, 1887, at the age of 86. A few days after suffering a stroke, he was eulogized by his friend and colleague Wilhelm Wundt. Adventures of Dr. Mises. Mises? Mrs.? Okay. Although Fechner was an outstanding scientist, there was a side of him that science could not satisfy. In addition to Fechner, the materialistic scientist, there was the Fechner, the satirist, philosopher, and mystic. For the young scientist to express so many viewpoints, especially because many of them were so seemingly incompatible with science, would have been a professional suicide. So Fechner invented a person to speak for his other half, and thus was born Dr. Mises, Mrs. A pseudonym for Dr. Mises first appeared while Fechner was still a medical student. Under this pseudonym, Fechner wrote Proof that the Moon is Made of Iodine. Cool. A satire on the medical profession's tendency to view iodine as a panacea. And in 1825, Dr. Mises published the Contemplative Anatomy of Angels, in which he reasoned, in which it is reasoned, tongue firm and cheek, the angels cannot have legs. Marshall, in 1969, summarizes the argument. Centipedes have God knows how many legs. Butterflies and beetles have 6. Mammals only 4. Birds, who all earthly creatures rise closest to the angels, have just 2. So, with each developmental step, another pair of legs is lost, and since the final observable category of creatures possesses only 2 legs, it is impossible that angels should have any at all. Dr. Mises also argued that because the sphere is the most perfect shape, angels are perfect, angels must be spherical, but planets are also spherical, so angels must be planets. All right. There followed a little book of life after death, Nana, or concerning the mental life of plants, and Zend Avestra, or concerning matters of heaven and the hereafter. In all, Dr. Mises was heard from 14 times in 1821 to 1876. Fechner always used Dr. Mises to express the day view. The view that the universe is alive and conscious. Always behind Fechner's satire or humor was the message that the day view should be taken seriously. Marshall, in 1969, makes this point about the Zend Avesta. Indeed, in Zoroastrian dogma, Zend Avestra, the living word, and Fechner was to intend that his own Zend-Avestra should be the word which would reveal all nature to be alive. In this work, Fechner argues that the earth is ensouled, just as the human being is, but the earth possesses a spirituality which surpasses that of her creatures. In fact, it was the Zend-Avestra, that sounds good, Avestra, that Fechner first described what would later become psychophysics. Fechner laid down the general outline of his program, Psychophysics, the Zend-Avestra, the book about heaven and the future life. Imagine sending a graduate student to psychology nowadays to the divinity school for a course in immortality as preparation for the advanced experimental work in psychophysics. How narrow we have become. In the little book of Life After Death, written to console a friend who had just lost a loved one, Dr. Mises described human existence as occurring in 3 stages. Let's find out. The first stage is spent alone in the continuous sleep in the darkness of the mother's womb. And the second stage, after birth, is spent alternating between sleeping and waking in the company of other people. During the second stage, people often have glimpses into the third stage. These glimpses include moments of intense faith or institutions that cannot be explained by one's life experiences. Dr. Mises tells us that we enter the third stage of dying. The passing from the first to the second stage is called birth. The transition from the second to the third is called death. Just as unborn children cannot foresee their forthcoming experiences in 2 stages, people cannot foresee their forthcoming experiences in 3 stages. In the third stage, one soul merges with other souls and becomes part of the Supreme Spirit. It is only during this stage that the ultimate nature of reality can be discerned. Whether as Dr. Mises or not, Fechner was always interested in spiritual phenomena. He was also interested in parapsychology and even attended some stances in which he experienced the anomalous movements of the bed, table, and even himself. His belief and involvement in parapsychology is clearly seen in the last book he wrote as Dr. Mises, The Day View as Compared to the Night View. Psychophysics. From Fechner's philosophical interest in the relationship between the mind and body sprang his interest in psychophysics. He wanted desperately to solve the mind-body problem in a way that would satisfy the materialistic scientists of his day. Fechner's mystical philosophy taught him that the physical and mental were simply 2 aspects of the same fundamental reality. Thus, as we have seen, he accepted the double aspecticism of Spinoza that Spinoza had postulated. But to say that there is more demonstrable relationship between the mind and the body is one thing. Proving it is another. According to Fechner, the solution to the problem occurred to him as the morning of October 22nd, 1850, as he was lying in bed. His insight into the systematic relationship between the bodily and mental experience could be demonstrated if a person were asked to report changes in sensations as the physical... Wait, I'm going to wrap my mind around this for a second. His insight into the systematic relationship between bodily and mental experience could be demonstrated if a person were asked to report changes in sensations as a physical stimulus was systematically varied. Fechner speculated that for mental sensations to change arrhythmically, the physical stimulus would have to change geometrically. What? In testing these ideas, Fechner created the area of psychology known as psychophysics. We're going to need more information. As was mentioned, Fechner's insight concerning the relationship between the stimuli and sensations was first reported in the Zend Avestria in 1851. Fechner spent the next few years experimentally verifying his insights and published 2 short papers on psychophysics in 1858 and 1859, and then in 1860 he published his famous Elements of Psychophysics, a book that arguably launched psychology as an experimental science. And then, as the name suggests, psychophysics is the study of the relationship between the physical and the psychological events. Fechner's first step in studying the relationship was to state mathematically what Weber had found and to label the expression Weber's law. Okay, so we have some math business here. It's got a triangle with a big R on top of another big R equals K, where, okay, so R, Ries, the German word for stimulus. In Weber's research, this was the standard stimulus, and the triangle with the R is the minimum change that in R that could be detected. That is the minimum change in physical stimulation necessary for a person to experience a JND. And K is a consonant we have seen. Weber found this consonant to be 1/40th of R for lifted weights. Okay, Weber's law about that. Weber's law concerning the amount of physical stimulus must change before it resulted in the awareness of a difference in or in change sensation, which is S. Although a series of mathematical calculations, Fechner arrived at his famous formula, which he believed to show the relationship between the mental and the physical, the mind and the body, which is S equals K log R. The formula mathematically states Fechner's earlier insight. That is, for sensations to arise arrhythmically, the left side of the equation, the magnitude of the physical stimulus must arise geometrically, the right side of the equation. This means that the stimulus gets larger, the magnitude of the change must therefore become greater. And greater if the change is to be detected. For example, if the stimulus, which is R, is 40 grams, the only difference is only 1 gram. A difference of only 1 gram can be detected. Whereas if the stimulus is 200 grams, it takes a difference of 5 grams to cause a J&D. In everyday terms, this means that sensations are always relative to the level of background stimulation. In a dark room, for example, turning on a dim light will be immediately noticed, as would a whisper in a quiet room. If the room is already illuminated, however, the addition of a dim light would go unnoticed, and would be a whisper in a noisy room. Okay. However, Fechner did not believe his formula applied to the evaluation of simple stimuli. He believed it applied to a more complex realm of human values as well. Our physical possessions have no value or meaning to us as inert material, but constitute only meaning for arousal within us as a sum of psychic values. In this respect, they take the place of stimuli. A dollar has in this connection much less value to a rich man than a poor man. It can make a beggar happy for a whole day, but it is not even noticed when added to the fortune of a millionaire. I see. The J&D as a unit of sensation. Fechner assumed that as a magnitude of stimulus increased from 0, a point which would be reached where a stimulus could be consciously detected. The lowest intensity at which the stimulus can be detected is called the absolute threshold. That is, the absolute threshold is the intensity of a stimulus at or above which the sensation results and below which no detectable sensation occurs. According to Fechner, intensity levels below absolute threshold do cause reactions. But those reactions are unconscious. In that it allowed for these negative sensations. Fechner's position was very much like those of Leibniz Petit's perceptions and Herbart threshold of consciousness. And for all three, the effects of stimulation cumulated, and at some point the absolute threshold was capable of causing conscious sensation. Fechner's analysis of sensation started with the absolute threshold, but because the threshold provided only one measure, it was of limited usefulness. What Fechner needed was a continuous scale that showed how sensations above the absolute threshold varied as a function of level of stimulation. This was provided by the differential threshold. Can't talk right now. Continuous scale, which is defined by how much stimulus magnitude needs to be increased or decreased before a person can detect a difference. It was in regards to the differential threshold that Fechner found that stimulus intensities must change geometrically in order for sensations to change arrhythmically. Given a geometric increase in intensity of a stimulus, Fechner assumed that sensations increased in equal increments, J&Ds. With this assumption, it was possible, using Fechner's equation, to deduce how many J&Ds above absolute threshold a particular sensation was at any given level of stimulus intensity. In other words, Fechner's laws assume that sensations increase in equal units, or JNDs, at the stimulus intensity increase geometrically beyond the absolute threshold. With this equation, Fechner believed that he had found the bridge between the physical and the psychical that he sought, a bridge that was scientifically respectable. Subsequent research demonstrated that the predictions generated by Fechner's equation were accurate primarily for the middle ranges of sensory intensities. Predictions were found to be less accurate for extremely high and low levels of physical intensity. Psychophysical methods. After establishing that mental and physical events were varied systematically and thus showing that science of the mind is indeed possible, contrary to the beliefs of such individuals as Galileo, Comte, and Kant, Fechner employed several methods to further explore the mind-body relationship, one of which is the method of limits, which he called the method of just noticeable differences. With this method, one stimulus is varied and is compared to the standard. To begin with, the variable stimulus can be equal to the standard and then varied, or it can be much stronger or weaker than the standard. The goal here is to determine the range of stimulus that the subject considers to be equal to the standard. The second one is the method of constant stimuli, also called the method of right and wrong cases. Here, pairs of stimuli are presented to the subject. One member of the pair is the standard and remains the same, and the other varies in magnitude from one presentation to another. The subject reports whether the variable stimulus appeared to be greater than, less than, or equal to the standard. And the third one is the method of adjustment, also called the method of average error. Here, the subject has control over the variable stimulus and is instructed to adjust the magnitude so that the stimulus appears equal to the standard stimulus. After the adjustment, the average difference between the variable and stimulus and the standard stimulus is measured. These methods were another of Fechner's legacies of psychology and are still used to this day. Fechner's contributions. In addition to creating psychophysics, Fechner also created the field of experimental aesthetics. Between 1865 and 1876, Fechner wrote several articles attempting to quantify reactions of works of art. For example, in an effort to discover the variables that made some works of art more pleasing than others, Fechner analyzed 20,000 paintings from 22 museums. After publishing his major work on aesthetics in 1876, Fechner spent the remainder of his professional life responding to criticisms of psychophysics. For another discussion on Fechner's experimental aesthetics, see Arnheim in 1985. Fechner did not solve the mind-body problem. It is still alive and well in modern psychology. Like Wegener, however, he did show that it was possible to measure mental events and relate them to physical ones. Some historians have suggested the beginning of experimental psychology is 1860 publication of Fechner's Elements. Although a good case can be made, most agree that another important step had to be taken before psychology could emerge as a full-fledged science. Psychology needed to be formalized as a separate discipline apart from both philosophy and physiology. As we will see in Chapter 9, it was Wilhelm Wundt who took that step. Summary. The discovery of individual... I'm over it. The discovery of individual differences among astronomers in the recording of astronomical events demonstrated the need, even within the physical sciences, for understanding of how the physical world was sensed and mentally represented. An intense investigation of the human sensory apparatus and the nervous system followed. Bell and Magadenji discovered that some nerves are specialized to carry sensory information. Highlight these notes. Carry sensory information to the brain, whereas they are specialized to carry sensory information from the brain to the muscles of the body. Mueller found each sensory nerve was specialized to produce a certain type of energy, which in turn produced a certain type of sensation. For example, no matter how the optic nerve is stimulated, it will produce a sensation of light. The same is true for all other sensory nerves in the body. Mueller's findings is called the doctrine of specific nerve energies. Helmholtz is a monumental figure in the history of science. He opposed the belief of vitalism. His teacher Mueller and others held. For Helmholtz, nothing was beyond scientific investigation. Ignoring the contention of specific nerve impulses that are too fast to be measured, he measured their speed and found that they are remarkably slow. Helmholtz differentiated between the sensations and perceptions, the former being of raw images provided as sense receptors, and the latter reflecting the meaning of past experiences, given those raw sensations. Through the process of unconscious inference, the wealth of prior experience we have had with objects and events is brought to bear our current sensations, converting them into perceptions. Helmholtz extended the doctrine of specific nerve energies to color vision by saying that specific receptors on the retina corresponded with each of the three additive primary colors, green, red, and blue-violet. For Helmholtz, all experiences of color could be explained as the stimulation of one or a pattern of three types of color receptors. Because Jung had earlier proposed a similar theory of color vision, the theory became known as the Jung-Helmholtz theory of color vision. Helmholtz also explained the auditory perception by applying a doctrine of specific nerve energies. He believed tiny fibers in the basilar membrane each respond to a different frequency, and that our auditory perception results from the combination of various fibers that have been stimulated at any given time. This is called the resonance place theory of auditory perception. Helmholtz's work clearly indicated that there is a difference between what is present physically and what is experienced physiologically. The reason for this difference is that the sensory equipment of the body is not capable of responding to anything that is not physically present. Although Helmholtz substantially mismatches between the present physicality and what is experienced psychologically, he did postulate an active mind and that takes whatever sensory information is available and creates the best possible interpretation of the extended reality. Helmholtz's work moved physiology closer to psychology and thus paved the way for experimental psychology. In his explanation of perpetual phenomena, Helmholtz sided with the empiricists, but Hering sided with the nativists. In his explanation of color vision, Hering postulated red-green, yellow-blue, and black-white receptors on the retina. Could either be torn down or built up. Torn down causing the color experiences of red, yellow, and white, respectively, and built up causing the experiences of green, blue, and black, respectively. Hering's theory could explain a number of color experiences that Helmholtz's theory could not. Lad Franklin proposed a theory of color vision based on evolutionary principles. Gall and Spurzheim expanded the faculty psychology into phrenology, claiming that faculties are housed in specific areas of the brain and an evaluation of a person's faculties could be made by examining the bumps and depressions on his or her skull. Phrenology became very popular because it aimed to provide an objective method of studying the mind, and because it seemed to provide practical information, many phrenologists believed that various faculties could be strengthened by practicing the activities associated with them. This belief resulted from formal discipline or the mental muscle approach to education. Florenz I fucking hate it when the words are split up like that. It's hard to read. Experimentally tested the conclusions of phrenologists had reached concerning the localization of brain function, and although he found some evidence for localization, the function of the lower parts of the brain, he concluded that the cortex itself acts as a whole. Using the clinical method, however, Barocca did find evidence for an area in the cortex responsible for the ability to articulate speech. Later, Wernicke discovered the cortical area responsible for speech comprehension. Furthermore, Fritz and Hitzig found the motor area on the cortex, and Ferrier further articulated the motor cortex and then mapped the cortical areas associated with the cutaneous senses of audition, olfaction, and vision. Thus, there did seem to be a localization function on the cortex, but the functions were not the same as the phrenologists had proposed, nor were they in the locations that the phrenologists had suggested. Weber was the first to attempt to quantify the relationship between physical stimulus and the sensations it caused. He determined the 2-point threshold for various parts of the body by observing the smallest distance between the 2 points of stimulation that would be reported as 2 points. Working with weights, Weber determined how much heavier or lighter the standard weight must be before it can be reported as being different than the standard. The sensation and the difference is called the just noticeable difference, J and D. Fechner expanded on Weber's work by showing that the J and Ds are not just related to stimulation in are related to stimulation in a geometric way. That is, the magnitude of the standard stimulus increases, so did the amounts that needed to be added to or subtracted from the comparison stimulus before these differences could be noticed. In addition to psychophysics, Fechner also created a field of experimental aesthetics. Now that it had been demonstrated that mental events could be studied experimentally, the ground was laid for the founding of psychology as an experimental science. The end.